Okay, here's a review of another limit problem. Ask us to find the limit as x approaches -2 of this equation. First step is you should substitute. So if I get -2 squared minus 7 times -2 minus 18, you'll notice you'll get 4 plus 14 minus 18, which gives me 0, over -2 plus 2 is 0. There's that indeterminate form. So that means I have to try to solve it another way. Doesn't mean that there's not an answer, just means I've got to solve it a different way. So I'm going to try this by doing my factoring. Well, if I notice the top factors to x minus 9 times x plus 2, because -9 times positive 2 gives me -18, and -9 times plus positive 2 equals -7, over x plus 2. You can see the x plus 2's, and now I can take the limit as x approaches -2 of that answer and find out, oh, the limit then has to be -11, -2 minus 9. Okay, here's a problem. It asks me to show that a function is continuous at x equals 2. Remember, there are 3 criteria for a function to be continuous. Number 1, f of c has to exist. The limit as x approaches c has to exist. And these two values have to be equal to one another. Okay? So I'm going to show that. Well, I got to show that f of 2, in this case, here's my value of 2 that I want to check for. Does that exist? And sure enough, because of that equals sign, it tells me what to do with x equals 2. So there has to be an answer. So no problem there. In order for the limit to exist, that means the left-hand limit has to equal the right-hand limit. The easiest way to do that is substitute x equals 2 into both equations and see what I get. So if you notice on the left side, I get 2 to the second plus 7. So that's 4 plus 7. So my left-hand limit is 11. When I plug it into the right-hand side, I get 9 minus 2 squared, so 9 minus 4, plus 6, which happens to also equal 11. So the left-hand limit exists, the right-hand limit exists, therefore the limit exists because they're equal to one another. So the function has to be continuous at x equals 2. Okay, here's a graph of this, and I will show that the function is continuous at x equals 2. So if I go up to from x equals 2, sure enough, I can draw that function without lifting up a pencil. I don't see any holes or asymptotes. And it turns out that the answer that I just showed here is 11. If I count up from the y-axis, that is at y equals 11. So sure enough, this function is continuous. Okay, let's take a look at something called numerical derivatives. Numerical derivatives are ways that calculators can approximate algebraic derivatives when we don't know what the equation is. Eventually, we're going to learn what the equation of some of these derivatives are, but right now, we don't know what they are. And so best we can do is look at an approximation by using numerical derivatives. For those using the TI-83 or T-84, you are using this notation, and you will find n derived by using the Math 8 button. You'll find Math and go down to Choice 8, and it'll be called n derived. And this is the notation that you use. You plug in the original equation in y1, the numerical derivative, which is in the equation, comma, the variable, which is almost always x, comma, we want to do it for all values of x. So that's why we have y1, comma, x. And you would actually generate what the graph looks like, even though we don't know what the equation is. For the inspire, this is how we input it in there. f1 of x is the original equation. f2, we use d dx, which is under the templates button. We've been using a lot for piecewise functions. And then we tell it to take the derivative of whatever we put in the first equation, f1 of x. And so when you get to class, you have a chance to practice that with the inspires. We're going to set up our window for x from -3 to 3 and y equals -8 to 8. And we're going to look at some features of this graph. We're going to try to see some relationships between the graph and its derivative, see if we can find the connections between the two graphs. Okay, so let's take a look at this. On the next slide, we'll take a look at what this graph looks like. So this is the graph of the function and its derivative on the inspire. I like the inspire because it's color-coded. So the blue graph is the original function. If you notice here, it's a cubic function. It starts low, does some same things in the middle, and then ends high. So starts low and ends high. Where the numerical derivative, if you notice, happens to be a parabola. Starts high and ends high. And that's a very recognizable shape. Hopefully we can recognize that as a quadratic function of some kind. Well, we want to see if there's some connections. So first thing I'm going to do is look at this derivative, and notice, I mean the original function, notice, well, this function initially starts out by increasing here. Then in the middle it actually decreases, and at the end it increases again. And if you notice here, it levels off here at the top. Okay, we call this, we introduced in class, the relative maximum. And it levels off at the bottom, which is actually called a relative minimum. And really interesting with the Inspire, if you trace along this, you'll actually see the word minimum pop up if you get the cursor right on top of that mountain, and you'll actually see the word minimum pop up if you get down to the very bottom. And we have some zeros that may or may not be significant, but if you trace along there, you'll see the word zeros occur wherever the original function traces along the x-axis. So I want to see if there's a connection between those features and the numerical derivatives. So remember, that's the red function. So if you notice, remember the original part of this function, it was increasing. If you notice, this part of the curve is above the x-axis. So that's a neat connection that you can make with a function that's increasing. The derivative has to be above the axis. And for the middle part of the curve, remember that function was going down, was decreasing, and that's where this function is below the x-axis. Everywhere here, it's below the x-axis, i.e. it's negative. And then over here to the right, again, the function was going up, and the red curve was always above the x-axis. Okay? So that's a connection. Whenever the original function is going up, we notice that the derivative is above the axis. Whenever the function is going down, like in the middle, we notice the derivative is below the axis. And likewise at the end, the function was going up. So the derivative was positive. Another keynote is to recognize that this mountain here corresponds to the 0 on the derivative. And likewise, this minimum corresponds to the 0. So there seems to be a connection between the mountain, I call them the mountains and the valleys, the top of the mountain and bottom of the valley, actually helps us predict where the zeros of the derivative are. And that's a very powerful connection that you need to make as we start to look at functions of this nature.